Has you ever stopped to think about just how much computing power is humming away all around us? And I don't just mean your phone or your laptop. I'm talking about, your washing machine, maybe the traffic lights on your commute, even that little digital watch. How do these things work? How do they have these brains? So today, in this deep dive, our mission is really to explore that hidden world, the often invisible computing that's going on. We want to kind of pull back the curtain on the brains inside these everyday objects, uncover the computational power that shapes so much of what we do.
Yeah, and we've pulled together some really good sources for this. We'll be looking at detailed stuff on computer architectures, embedded systems specifically, and also the whole process of chip manufacturing, which is pretty wild. It's going to be a journey into that unseen power that's, well, everywhere.
Okay, great. So let's start with maybe the most basic question. What's the fundamental difference between, say, the computer you might be listening on right now and the one in your microwave? Right, so on one hand, you've got what we call a general purpose computer. Think of it like a digital Swiss Army knife. It's super versatile, built for tons of different tasks. It can run almost any program you give it. Your PC, laptop, tablet, smartphone, that's classic examples. They're flexible. You can reprogram them for word processing, gaming, browsing, coding, anything really. Common in homes, offices. Hardware is usually pretty powerful, and it supports all sorts of software.
Exactly. And that really highlights the contrast with special purpose computers. These are the specialists. They're built for one specific job or maybe a very narrow range of jobs, and they do that one thing really, really well. Think about an ATM or a digital watch, like you said, or the controller in your microwave. These things aren't meant to run different apps. They have a dedicated function. And crucially, you usually can't just reprogram them yourself. They're optimized for efficiency, reliability in that one role. The hardware is tailored, and the software is often just fixed firmware. Very limited flexibility. So just to sum it up quickly, multiple tasks versus one specific task. High flexibility versus very low. PC or laptop versus ATM or washing machine. Cost-wise, general purpose is usually higher up front, but these special purpose ones, when made in huge numbers, can be incredibly cheap. And performance? One's broad, the other is totally task-specific. And understanding that difference is key. It explains why we have so many kinds of computers. But it raises the next question: how do they actually work differently inside?
That's a perfect transition. Yeah, it makes you realize computer isn't just one thing. So let's pop the hood and see what's inside. What are the core bits of a general purpose computer? Well, you've got the CPU, the central processing unit. That's the main brain doing the calculations, running the show. Then memory, RAM for temporary stuff, active programs, and ROM for the basic startup firmware. You talk to it with input devices, keyboard, mouse, mic. It talks back with output devices, monitor, printer, speakers. For long-term storage, you have storage devices like hard drives, SSDs, flash drives. Everything's connected on the motherboard, the main circuit board. You need a power supply unit for electricity. And the operating system, like Windows or Linux, manages all that hardware and software working together.
Right. Now compare that to a special purpose computer. Everything's streamlined, optimized. Instead of a big CPU, you often find a microcontroller or an embedded CPU. It's kind of like a mini computer on a single chip CPU, memory, I/O, all integrated, designed for specific control tasks. The memory is usually ROM or maybe EEPROM, holding that fixed program, the firmware. Not usually user changeable. Input often comes from sensors, temperature, motion, that kind of real world data. And output goes to actuators, things that do physical stuff like turning on a motor, updating a display, power supply, often just a small battery or low voltage DC. Very efficient. The software is that embedded firmware built for just one job. And sometimes they might have a communication interface, things like UART, SPI, I2C. These are just ways for chips to talk to each other locally, share data. Not always needed for the simplest devices, though.
It's really fascinating how tailored they are. Okay, so components differ, but the real brain difference is the processor. Right? Let's compare a standard CPU to these specialized ones. So the CPU, the central processing unit, again, that's your classic general purpose processor, built for everything and anything. Key things are versatility, multitasking. It handles math, logic, control, I/O, all of it. We're talking Intel Core i5, AMD Ryzen, Apple's M-series chips, ARM Cortex-A series in phones. These are in your laptops, desktops, servers, smartphones. Running browsers, games, complex software.
Right. And then you have special purpose processors. These are custom designed, often embedded, and built for pure efficiency at one task. They're dedicated. And because of that, they're often much faster and way more power efficient for their specific job than a general CPU could ever be. Like a GPU, graphics processing unit. Think NVIDIA RTX cards, built just for rendering images, video. Great for gaming, but also huge in AI now. Or a DSP, digital signal processor. Your phone uses these, like Qualcomm's Hexagon, for handling audio, video signals efficiently. Google has its TPU, Tensor Processing Unit, purely for machine learning in their data centers. Even your network card has an NIC processor, focusing just on network packets. And then the embedded controllers we mentioned, ML, AVR, STM32, ESP32, those are everywhere in appliances, IoT, gadgets. You even get ASICs, application-specific integrated circuits designed for one single algorithm, like Bitcoin mining chips. These specialists are in drones, smart TVs, washing machines, routers, medical gear, robots, you name it. So, quick comparison. CPU is general purpose, SPP specific. CPU is highly flexible, SPP is low flexibility. Speed-wise, a CPU is slower for specialized tasks, while an SPP is optimized and faster for that task. Architecture. CPU complex, SPP simplified. Cost. CPU relatively high, SPP varies but often cheaper in bulk. And power efficiency. SPPs, especially embedded ones, are usually much better for their specific job. What's really key here is this tailoring. It's not just a tech detail, it's what makes tiny, cheap, low-power, single-function gadgets possible.
That really clarifies things. It explains the invisible computer world. Okay, let's zoom in on some of those embedded controllers you mentioned. These are the real drivers behind smart devices, right? It's amazing what they pack in. Let's start with the Atmel AVR. The ATmega 328P is probably the most famous one. It's an 8-bit RISC chip, and it's the heart of the Arduino Uno board, which so many people start with. Super easy to use, very beginner-friendly, great for basic DIY stuff, simple robots, controlling LEDs, simple automation. Downside, limited power and no built-in Wi-Fi or Bluetooth. You need extra modules for that. Then you step up to something like the STM32 family from STMicroelectronics. These are way more powerful. Use a 32-bit ARM Cortex-M core. There are tons of models. For the popular, affordable STM32F103, people call it the blue pill, up to really high-end ones. They offer serious performance and lots of built-in peripherals. CAN bus for cars, good ADCs for sensors, PWM for motors, so you see them in drones, industrial controls, motor drivers, medical devices. The catch: a bit steeper learning curve for beginners compared to AVR, just because there's so much more there. But then there's the ESP32 from Espressif Systems. This one's a beast, especially for connectivity. It's a 32-bit dual-core chip, but the killer feature is built-in Wi-Fi and Bluetooth. That makes it incredibly popular for IoT projects, wireless sensors, home automation, smart farming, anything needing wireless comms. It's cost-effective, powerful, maybe uses a bit more power than an AVR, but you get so much more capability built right in.
Yeah, comparing them side by side. AVR is 8-bit, maybe 16 megahertz, no built-in connectivity. STM32 is 32-bit, much faster, 72 up to nearly 500 megahertz sometimes, with standard interfaces like USB, SPI, I2C. ESP32 is 32-bit dual-core, up to 240 megahertz, but the Wi-Fi and Bluetooth are the big deal. Flash memory goes from maybe 32 KB on the AVR to up to 4 MB on the ESP32. So AVR for simple stuff, STM32 for mid-level embedded. ESP32 really targets IoT and smart devices. Arduino loves AVR. Drones often use STM32, and ESP32 is huge in smart homes. Which brings up a really interesting point. Why did these ESP chips in particular become such a massive deal for the Internet of Things?
That's a great question. Because I remember not too long ago, adding Wi-Fi to a project was a real pain. Expensive, complex. These ESP chips just blew that wide open. Let's dive into the ESP32 first. It's this incredibly low cost, low power, but still really high performance microcontroller from Espressif, based in China. It's pretty much the go-to chip now for IoT, automation, wireless projects. It made advanced stuff accessible. Look at the features. 32-bit dual-core extensive processor, up to 240 megahertz. That's a lot of power. But the magic is that built-in Wi-Fi, 802.1BEN, and Bluetooth, both classic and BLE, Bluetooth Low Energy. Plus, loads of GPIO pins, usually 30-something, 4 megabytes of flash for your code, 520 kilobytes of SRAM, operates at 3.3 volts. It's got analog to digital converters, digital to analog, all the standard communication interfaces, UART, SPI, I2C, PWM, even CAN bus on some, and built-in security features too. And developing for it is super flexible. You can use C++ with the Arduino IDE, which is really popular, or MicroPython, Lua, even JavaScript. There's Espressif's own framework, ESP-IDF, or the Arduino core for it. Lots of tools support it, Platform.io, VS Code. You find it in modules like the standard ESP32, Room32, the Rover with extra RAM, the NodeMCU boards that plug into breadboards, even the ESP32 CAM with a camera interface. Applications everywhere. Smart lights, locks, wearables, industrial sensors, Wi-Fi robots, remote health monitors, smart irrigation. That's huge. And before the ESP32, there was its predecessor, the ESP8266. This chip really started the whole affordable Wi-Fi revolution for hobbyists and makers. It's a tiny, dirt-cheap Wi-Fi microchip you can get modules for like $2, with the whole networking stack built in. Suddenly, adding Wi-Fi to anything became incredibly easy and affordable. Specs-wise, it's a 32-bit Tensilica single-core CPU, usually 80 MHz, but you can push to 160. About 160 kilobits of RAM, flash from 512 KB up to 4 MB, runs on 3-point-something volt. Fewer GPIO pins than the ESP32, maybe 17 max, depending on the module. But the key thing was that built-in Wi-Fi. You saw it in modules like the tiny ESP-S01, the ESP12 versions with more pins, and the popular NodeMCU ESP8266 port. Programming was easy too, especially with the Arduino IDE add-on. Or Lua, with NodeMCU firmware, MicroPython, or just using AD commands to control it as a modem. And it had good power-saving sleep modes, vital for battery-powered IoT stuff. People used it for smart switches, Wi-Fi remote controls, sending sensor data online, simple IoT nodes, door sensors, tons of things.
Yeah, comparing them directly. ESP8266 is single core. ESP32 is dual core. Both have Wi-Fi. Only ESP32 has Bluetooth. ESP8266 has fewer GPIO pins, fewer lower resolution ADC channels compared to ESP32. Less RAM on the 8266, about 160 kb versus 520 kb plus options on the ESP32. Both are power efficient, but ESP32 generally has more advanced power management cost. ESP8266 is ridiculously cheap. ESP32 is slightly more, but still incredibly affordable for what it does. What's really amazing is how Espressif packs so much more into the ESP32, dual cores, Bluetooth, more peripherals, while keeping the price point so low. That wasn't just an iteration. It truly democratized IoT development. And to really get how these chips work so efficiently, especially something like the ESP8266, we need to touch on the architecture inside. That Tensilica Extensa L106 core in the ESP8266, it's based on RSC, reduced instruction set computing. So why RSC? Well, think of it like giving instructions. You could have one very complicated instruction that does many things, or lots of very simple, fast instructions. RAC chooses the simple, fast route, uses a smaller set of optimized instructions. Each one is designed to execute really quickly, often in just one clock cycle. Simplicity leads to speed and efficiency. The Extensa core itself is kind of modular, though the L106 version in the ESP8266 is fixed. It's designed for high performance per watt, very streamlined. It's a great fit for the ESP8266 because it allows for a small chip, low power draw, and the real-time processing needed to handle all the Wi-Fi communication stuff reliably. The instruction set itself is typical RISC, fixed length instructions mostly. It uses a load store approach basically. Data only moves between the main memory and the chip's internal fast storage registers using specific commands. All the real work happens fast, right there in the registers. It has instructions for basic math, logic, moving data, controlling program flow, plus some neat tricks for handling loops efficiently and responding super quickly to external events interrupts.
Okay, so these incredibly complex little brains, they don't just pop out of nowhere. The manufacturing process itself is mind-blowing, almost like science fiction when you hear about it. Yet chip manufacturing is this multi-stage process involving design, fabrication, packaging, testing, all on these silicon wafers. It's unbelievably precise. It starts with design, the front end. Engineers figure out the chip's architecture, what it needs to do, design the logic using languages like Verilog or VHDL. Then they simulate and verify like crazy. Got to catch bugs before you build millions of them. Then comes fabrication. The back end. This happens in huge super clean factories called foundries or fabs. They start with ultra pure silicon wafers, thin disks. Then photolithography. This is key. They use UV light and masks to project microscopic patterns onto the wafer, layer by layer. It defines where transistors and wires will go. Then doping to change the silicon's electrical properties and etching to remove material. This builds up billions of tiny transistors, usually using CMOS technology that's standard for modern chips. Finally, they add layers of metal interconnects, like tiny copper highways, to wire everything together. After the wafer's done, it's packaging and assembly. The wafer is diced into individual chips, or dies. Each tiny die goes into a protective package, the black squares you see on circuit boards. Fine wires connect the die to the package pins. Last step, testing. Rigorous electrical tests, burn-in stress tests to find weak spots. Not all chips make it. The percentage of good ones is called the yield, usually pretty high, like 70–90%, but defects happen. The big players here, the foundries, are companies like TSMC in Taiwan. They actually make the Espressif chips, often on older but very reliable 40 or 55 nanometer processes. Samsung, Intel, Global Foundries, Pike in China. These are the giants. And those technology nodes like 180 millimeter for old chips, 55 millimeter for stuff like ESP32, or down to 7 millimeters or less for cutting-edge CPUs. That number refers to the scale. How tiny the features are. Smaller means more transistors, faster speeds, better power efficiency.
It's an incredible feat of engineering, and it all comes back to the fundamental way most computers work, based on the stored program architecture or the von Neumann architecture. This idea from John von Neumann way back in 1945 is still the foundation for almost everything, desktops, phones, even these microcontrollers we've been talking about. The core idea is simple. The program instructions and the data the program uses are stored together in the same memory space. You have a memory unit, a control unit to fetch and figure out instructions, an ALU arithmetic logic unit to do the math, I/O units, and some fast temporary storage called registers, and it runs in a constant loop. Fetch an instruction from memory, decode what it means, execute the operation, and repeat. Fetch, decode, execute. It's powerful because programs are just treated as data, execution is generally step by step, and the hardware can be simpler because code and data share the same pathways, the same bus. But that leads to the famous limitation, the von Neumann bottleneck. Because the CPU and memory share that same data bus, that single pathway, it can't fetch the next instruction and fetch data for the current one at the exact same time. It creates a kind of traffic jam limiting speed.
Like a bottleneck, right. So a 1945 concept still rules, but with this built-in limitation. Is that becoming a major problem now with things like AI needing so much data? Or have we found ways around it?
That's a really good question. And yes, it's absolutely something engineers constantly fight against. The basic architecture is still there, but modern systems use tons of tricks to mitigate it. Things like much faster memory, complex caching systems right on the CPU chip to keep frequently needed data and instructions super close. That helps a lot. Some specialized systems, especially in embedded, might use a Harvard architecture, which actually does have separate pathways for instructions and data. And things like multi-core processors, parallel processing, and offloading tasks to specialized processors like GPUs, that all helps bypass the bottleneck for certain kinds of work. So yeah, it's a known issue, but we're always finding clever workarounds.
Okay, that makes sense. So we've covered general versus special purpose, dug into embedded controllers like the ESP series, seen how chips are made, and looked at the underlying architecture. What does this all lead to? Where is this taking us? Well, it all points towards this idea called ubiquitous computing, or UbiComp. Basically, it's computing that's everywhere but invisible. It just blends into the environment, into everyday objects. It's not about sitting down at a computer anymore.
Exactly. It has a few key traits. Invisibility is when the tech fades into the background. Context awareness devices sense their environment, your actions, and adapt. They might anticipate what you need. It heavily relies on those embedded systems we talked about, the tiny computers and everything, forming the Internet of Things, IoT. That's the hardware backbone. The computing power is always available, often without you needing to actively interact with it. And connectivity is crucial. Devices talking to each other, to the cloud, via Wi-Fi, 5G, Bluetooth, Zigbee. If you think about the enabling technologies, it's IoT, wireless networks, sensors, actuators, cloud computing, AI, and machine learning. These are all feeding into the rise of UbiComp.
And you see examples everywhere now, right? Home automation, smart thermostats like Nest, smart lighting, Alexa or Google Home, healthcare, wearable monitors, smart insulin pumps, beds that track sleep, transportation, GPS navigation, smart traffic lights, parking sensors, retail, shelves that know when they're empty, automated checkout, even education with smart boards or workspaces with smart conference rooms. It's creeping in everywhere.
For sure. The advantages are obvious: convenience, efficiency, safety, automation, less manual effort. But there are real challenges too. Privacy is a big one. All these devices collecting data, where does it go? Who owns it? Security is another huge challenge. Every connected device is a potential entry point for attacks. Interoperability, getting devices from different companies to actually work together smoothly, can be tough. And power consumption. Keeping all these always on or sensing devices running, especially on batteries, is a constant engineering problem. It really brings up a critical question. As this tech becomes more invisible, how do we make sure we stay in control? How do we understand what it's doing rather than just letting it happen around us?
Wow. What a journey in this deep dive. We went from the basic difference between the computer on your desk and the one in your microwave, right through to specialized chips like the ESP32 that power the IoT. We saw the incredible complexity of making these chips and how it all still connects back to von Neumann's ideas from decades ago. And it all culminates in this idea of ubiquitous computing where the technology just melts into the background.
Exactly. And as these embedded systems, this ubiquitous computing weaves itself deeper into our lives, blurring digital and physical, it really makes you think about our relationship with technology. It's shifting from something we actively use to something that's just present. The final thought, perhaps, is how do we ensure this omnipresent technology genuinely serves us, empowers us, rather than subtly starting to direct us or shape our choices without us even realizing it?